Welcome friends to this lecture on computer aided power system analysis. We have been looking into the aspect of transformer modeling. In the last lecture we have looked into the case where we have considered an YG0 transformer, and then we have looked into the process of deriving this transformer admittance matrix. Now, to continue with this, let us today consider another transformer connection, and let us today we consider a transformer connection YG2. So, what does it mean? That here in this case also the primary side is connected in star grounded and the secondary side is connected in star grounded, but now there is a phase difference between the phase A voltage of primary side and the phase A voltage of secondary side, which is equal to 2 into 30 degree, that is equal to 60 degree. So, that is the case. So, then now there is a phase difference. So, now as before, let us consider that this 3 phase transformer consisting of 3 single phase transformers. So, then we have got 6 windings and they are connected in this fashion. So, we have got 6 windings. We are doing exactly the same what we have done in the last lecture. So, we are saying this is A1, A2, this is small a1, small a2, these are the terminals, B1, B2, this is small b1, small b2, this is capital C1, capital C2, this is small c1, small c2, and let us assume that the dots are here, and we already discussed what is this dot convention means. So, these we have got these dots and we have got these dots. So, these are the 3 dots. So, we have not made any connection, we have simply collected these 3 transformers and we have simply collected these 6 windings. Now, we have to make a connection. So, for that let us first draw the phasor diagram. So, phasor diagram would be something like this. So, first is this and this. So, this is grounded. So, let us say that this is A1 and this is A2 and this is let us say B1 and let us say this is B2 and this is capital C1, this is capital C2. So, then what we are saying as before, that we are simply connecting A2, B2 and C2 terminals together at the primary side, and then we are connecting that shorted terminal to ground. So, let us make that connection. So, what we are doing is, as before, we are up to this point we are doing the as before. So, we are simply connecting these 3 terminals together and grounded, and then we say that this is my phase A, this is my phase B, this is my phase C. So, then therefore, we say that this is my phase A, this is my phase B, this is my phase capital C. So, our connection at the primary side is over. So, now at the secondary side, now in the secondary side this is also connected it star grounded, but the difference is that now there is a difference of 60 degree phase between phase A voltage and of the primary side and the phase A voltage of the secondary side. So, that we have to consider. So, then therefore, what we do is let us draw dotted lines and let us draw another dotted line. So, let us draw a dotted line. So, these are the just for these, I mean dotted lines are the for the reference. Now, so I mean this is the phase A voltage of the primary side, and the secondary side phase A voltage would be 60 degree lagging behind it. So, then secondary side phase A voltage would be simply here, something like this, and this angle is 60 degree, this angle is 60 degree. So, this would be the secondary side phase A voltage. Now, secondary side phase B voltage would be 120 degree lagging to this. So, then this would be the secondary side phase B voltage. So, this is secondary side phase A voltage, secondary side phase B voltage, and secondary side phase C voltage would be 120 degree lagging from this. So, then it also would be somewhere like this. So, it would be something like this. So, it would be secondary side phase C voltage, and this angle would be nothing but equal to 30 degree, right. So, we have located the phase A voltage, phase B voltage, phase C voltage of the secondary side. Now, we have to mark the terminals. Now, for marking the terminal, we need to understand one thing, we actually need to recollect one thing, that when we say that these two voltages are in phase. So, that means they are not only in parallel, but their orientation is also parallel. So, then therefore, if I say that this voltage VA1 A2 is in phase of VA1 Vs A2. So, then therefore, if I draw these two parallel lines, so it will denote A1 and this denote A1. So, then therefore, if this denotes A1 and this denotes A2, and because these two are in phase, so then therefore, this also should denote A1 and this also should denote A2. So, then it means that they are in parallel and in phase. On the other hand, for example, if we said that these two are in anti-parallel, so then in that case what would have been the case? In that case, the case would have been this and this. So, then it would have been, so this is A1 A2 and anti-parallel is something like A1 A2. So, then therefore, when two phases are, so then when two voltage vectors are in parallel, so then therefore, or rather when two voltages are in phase, so then therefore, those phasors would be not only in parallel, but their orientation would also be the same. So, then therefore, so now let us see. So, now let us look at that what are the two parallel vectors. Now, if I look at this vector and this vector, obviously this vector is parallel to this vector, right. I mean this vector is parallel to this vector. Now, if this vector is parallel to this vector and if this has to be in phase, so then therefore, we would say, so then therefore, if this is capital C1 C2, so then therefore, this also should be small c1 and C2, because this voltage and this voltage they are in parallel, and so then therefore, if this voltage is C1 C2, so then therefore, this voltage also should be small c1 and C2, because these two are in parallel and in phase, because we have put these dots like this. Similarly, this and this would be in parallel and their orientation also should be the same. So, then therefore, this would be small a1 and this would be small a2, right, because their orientation would be also be the same. So, then therefore, this top point is a1, here also this top point is small a1 and similarly a2, and this vector is parallel to this vector, and because these two have this dots here like this. So, then therefore, this would be small b1 and this would be small b2, right. So, these are the marking of the different terminals, and so then therefore, we say that this is actually our phase A, and we say that this is my phase A, this is my phase B, and this is my phase C. And of course, because this is grounded, so then therefore, this terminal also should be grounded. So, then what? So, then from this phasor diagram what we are seeing? this phasor diagram tells me that if we wish to realize a transformer of this type of vector connection, here we should connect A1, B1, C1 and together and ground that particular shorted terminal, and we should take and we should denote terminal C2 as phase A, and we should denote terminal A2 as phase B, and we should denote terminal B2 as phase C, correct. So, if we do so, so now here if we do so, it would be a little more complicated. So, then to actually realize it, I mean let us again redraw this diagram. So, what we have got is A1, B1, so we have got A1, A2, B1, B2, C1, C2, and we have dot here, and what we have here is we now say A2, A1. So, this dot would be, now we are just simply putting this winding in a reverse manner. Similarly, we say that this is B2 and this is B1. So, then this dot would be here and this dot is here. Please note that these dots are still at capital B1 and small b1 terminal as here. So, we have not changed these dot points. What we have done, we are simply putting this winding in a reverse fashion, nothing else. So, we are simply putting this winding in a reverse fashion. So, we have got C2, got C1 and this dot is here and this dot is here. So, we again make this connection. So, in the primary side, at the primary side what we have, we simply make these connections together. So, these are connections together, and this we say at phase A, this we have just now seen, this is phase B. So, this is phase C. Now, at the secondary side, this phasor diagram tells me that A1, B1, C1 should be connected together and again shorted to ground. So, what we are doing, A1, B1 and C1 we are connecting together and making it to ground. Then what we are saying that A2 should be denoted as phase B. So, it is actually phase B. Then B2 should be denoted as phase C. So, B2 should be denoted as phase C, and C2 should be denoted as phase A, right. So, this is the, so then from this vector diagram we have got this connection. So, this connection is made. So, then therefore, now this point potential would be, because these are, so this would be V capital A, right, this would be V capital B, this would be V capital C. And what would be this voltage? This voltage would be actually 0 minus this, because now essentially what will happen, because there are dots together. So, when this is positive, this is positive. So, then therefore, this is actually negative. So, then we can say that this is actually minus VB. So, we can say that is this actually minus VC and this is minus VA, because this is grounded. So, then therefore, at every time this should be positive to this. So, then therefore, if this VC is positive to corresponding to this grounded, so then therefore, at which is 0. So, then therefore, if this is 0, so then therefore, this should be negative, because this point should be positive to with respect to this. So, then therefore, these are denoted. So, then these voltages will be minus VB, minus VC and minus VA. And now we denote this currents as IA, IB, IC, capital C, right. These currents are IA, IB and IC, and here this current should be I small b, current should be I small c, I small a. As usual, transformer is 1:1, transformer is 1:1. So then therefore, so with this all this notation and this connection, and we have denoted all these voltages and currents. So then therefore, now we are ready to write down the equations. So then what would be the equation? Equation would be IA into Y, Y is again this transformer leakage admittance, would be VA minus of this voltage minus of VB. So that means it would be Y into VA plus VB. Similarly, what would be IB? IB is Y into VB plus V small c, VB plus small c. I capital C is Y into VC plus small VA. Right. Now, what happens to this current? Now, if we recall the dot convention of any transformer, if we recall the dot convention of any transformer, what this dot convention says? For example, here if I say that this current is IP and if I say that this current is IS, we say that IP and IS they are in phase. What does it mean? That the current entering the dotted terminal, dot terminal at the primary side would be in phase with the current leaving the dot terminal at the secondary side. I repeat that this dot convention says that this current entering the dot terminal at the primary side would be in phase with the current leaving the dot terminal at the secondary side. Now, here what happens? Here what happens? Here this current is IA is entering the dot terminal, but the current IB is actually entering these dot terminals. Please note that if this current is IB here, so then therefore this current should be IB here. Similarly, this current is also entering this dot terminal here, and similarly this current is also entering the dot terminal here. So then therefore, this current and this current they would be out of phase each other. So then therefore, I can write that I capital A is equal to minus IB, I capital A is equal to minus IB, or I can say that IB is equal to minus IA, and minus IA means minus of Y into VA plus VB, right. Similarly, I can write down that I capital B is equal to minus I small c, and this minus I small c. So, therefore, I c is equal to minus I b, and minus I b is equal to minus y into V b plus V c, and I capital C is equal to minus I a, or in other words I a is equal to minus of capital I c, or in other words I small a is equal to minus of y into V c plus V a, right. So, then therefore, these are the 6 equations we have got now. So, now with these 6 equations, now we are now ready to find out the Y bus matrix. We are now ready to find out the Y bus matrix. Now, again as usual, our I primary now if I say, so now our I primary ABC is nothing but I capital A, I capital B, I capital C T, and our I small ABC would be, please note, now here at these terminals these currents are outgoing, but I again repeat, we again have to recollect that what we have done is, what our convention is, that if I have a transformer between two buses, if I have a transformer between two buses, then our convention is that these two currents would be always entering the transformer from both the sides. So, then therefore, Is ABC would be is equal to minus Ia minus Ic and minus Ib, minus Ia minus Ib and minus Ic. So, then therefore, Is ABC would be minus Ia minus Ib minus Ic transpose, and so then therefore, V and Vp ABC is Va, Vb, Vct, please note that this is capital, and Vs ABC is V small a, V small b, V small c. So, now if I now write down the Ia, Ib, I capital C minus Ib, minus Ia minus Ib minus Ic, so that is equal to Va, Vb, V capital C, Va, Vb, V small c. Now, what is Ia? Ia is again y into Va plus Vb. So, there should be one y and Va plus Vb. So, this is 1, then 0, then 0, Va plus Vb. So, then 0 and 1 and 0. Ib is y into Vb plus Vc, y into Vb plus Vc. So, this is 0 Vb. So, 1, 0, 0, 0, 1. So, these are all 1, all 1. What is Ic? I capital C, y into Vc plus small a. So, it is 0, 0, 1, Vc plus small a. So, this and this. So, then this is 1, 0, 0. And now, what is minus Ia? Sorry, now what is minus Ia? Now, if Ia is equal to y into Vc, if Ia is equal to minus y into Vc plus, so minus I would be y into Vc plus Va. So, then y into Vc plus, so minus Ia is equal to 0, 0, 1, 1, 0, 0, minus Ib. What is minus Ib? Minus Ib is y into Va plus Vb, y into Va plus Vb, y into Va, Va plus then Vb, Vb, then 0, and minus Ic is y into Vb plus Vc, y into Vb plus Vc. So, 0, 1, Vb, Vb, plus V C. So, this is the matrix. So, again here we again denote that this is IPABC. So, this is IPABC. So, this is IPABC. This is ISABC, ISABC. This is VP ABC, and this is VS ABC. So, now we make the partition. We now make the partition. So, this is the partition. So, then obviously a Y. So, this 3 cross 3 matrix would be Y1, this 3 cross 3 matrix would be Y2, this 3 cross 3 matrix would be Y3, and this 3 cross 3 matrix would be Y4. So, then Y1, so Y1 is nothing but I3. We can see that it is an identity matrix of 3 cross 3, and what is I3? I3, I repeat that it is a 3 cross 3 identity matrix. Similarly, Y4 is also here I3, a 3 cross 3 identity matrix. Y2 is 0 1 0 0 0 1 1 0 0. So, Y2 is 0 1 0 0 1 0 0 0 1 and 1 0 0 0 0 1 and 1 0 0. So, this is Y3 to Y3 0 0 1, then 1 0 0 1 0 0 and 0 1 0 0 1 0. So, these are the 4 matrices. And one very important observation is that Y2 is transpose. So, these 2 matrices are actually transpose of each other. So, this is a cross check for a correct transformer modeling, right. So, this this particular 3 cross 3 matrix and this particular 3 cross 3 matrix should be always a transpose of each other, especially if there is no phase shifting tap. If there is no phase shifting tap, so then this this 3 cross 3 matrix and this 3 cross 3 matrix should be transpose of each other. So, then therefore, so this is how the transformer modeling is to be done. Again here, as we can see that we have really not taken any kind of assumption. We have started with this transformer connection. From this we have deduced that this what is the phase difference between the phase A voltage of primary side and secondary side, and from that we have first taken all these particular terminals together without making any connection. Then we have first drawn the phasor diagram of the primary side, indicated the terminals, and from this terminals indication we have done this connection. Then we have drawn the phasor diagram of the secondary side, and then also indicated the transformer, taking into account the basic operation of any transformer as well as the basic concept of a parallel phasor representation. From there we have made the connection, and once we have made the connection, then we have noted down all these voltages and currents, and these voltage and currents sign of these voltages and currents we have made according to the standard dot convention. So, once we have made all these voltages and currents, or rather once we have essentially denoted all these voltages and currents properly, taking into account this standard dot convention, after that we have simply written down the equations, and then from there we have found out the transformer admittance matrix. So, then therefore, we can find out that to model a transformer, actually nothing is to be remembered, it can be done in a very easy step by step manner. So, we stop today. In the next lecture we will again try to see some other example if possible. Thank you.